Welcome back. We're still talking about linear transformations. Now we're talking specifically about properties of linear transformations. So this piece that I left for last actually has an overall theme. We've talked about a times x equals b, having solutions for every b in Rm. And we've also talked about how it has unique solutions. And I want to know what that looks like in the context of linear transformations now that we have t of x equals a of x. So first definition we're going to talk about is a linear map T is called onto, or surjective if you want to be fancy, if each vector B in Rm has an image, which means it gets mapped to, by at least one x in Rn, such that T of x equals B. So what that's implying is, we're going to use some of the definitions from last time, is the image of T is all of Rm. That should sound kind of familiar. We talked about a of x equals b having solutions for every b in Rm. That's how we can rephrase this. Sorry, I had to think about where I was going. This is how we're going to rephrase it. We can say that if t of x is equal to a of x, then we say t is onto if and only if a of x equals b has a solution for all b in Rm. Next definition that we're going to look at, we've got a linear map, still going from Rn to Rm, and we're going to call it one-to-one, or injective if you're fancy, if each b in Rm is the image of at most, this time we don't want any more than one x, such that t of x is equal to b. So what this is implying is if t of x1 equals t of x2, then x1 equals x2. The way I always think of it is, if the outputs are equal, then the inputs are equal. It's not and you can think of it the other way around. If the inputs are equal, then the outputs must also be equal. But in order to prove things, we need to think of it this way. We need to think of it, if the outputs are equal, then the inputs are equal. If you haven't seen onto and one-to-one before, but you're going to take more math classes, get really comfortable with these definitions because they're going to pop up over and over and again. In the context of linear algebra, we can rephrase the one-to-one using a times x. We can say if t of x is equal to a of x, then we say t is injective. Oh, I meant to write one-to-one. If and only if ax equals b has a unique solution or no solution. Save that because I felt like that was a little bit confusing, so I saved that. Why is that? Because I said at most 1x. And so no solution falls underneath the category of 1 or less. Okay, let's look at an example. We have T is mapping from R4 to R3, and we have the standard matrix A, which means we now know how T is being defined. And we want to know, is T onto, is it one-to-one? Let's start with onto. Let's remember what onto means. Onto means, let's see. So onto, then ax equals b has solutions for all b. And then we had a theorem that gave us the conditions for this to be true. If you don't remember, it's in section 1.4, and then it should have been labeled theorem 4, but I'm not sure if I did that. It's called the equivalent statements of A, If you don't remember it, please pause, flip back, look at it, and then come up with an answer for what conditions we need for onto. Okay, so we're going to say A has a pivot in every row. See, pivot, 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 every row. So that implies that for all B in Rm, Ax equals B has a solution. Then that implies T is onto. Okay, now we want one-to-one. One-to-one, I told you that A needed to have a unique or no solution. Does A have a unique or no solution here? You can tell by looking again at the pivots. A has a free variable. What does that mean about the number of solutions A has? So A has infinitely many solutions. So then T is not one-to-one. Okay. So that is how we can use things we know about A to prove one-to-one and onto-ness of T. Let's go ahead, let's do it again. Now we have a different matrix. We're going to go from R2 to R4, and we want to know, is T onto or one-to-one? Same idea. So we have A doesn't, we're going for onto first. Maybe I should label that onto. A doesn't have pivots in every row. So that means Ax equals B does not have solutions for all B, which means T is not onto. And then we're going to go and do one-to-one. So now we want to have a unique or no solution, which means we need to look at A. We need to look at the pivots of A. Now we can say A has no free variables. So notice that doesn't say anything about whether it's going to have a solution or not. It just tells us if it has a unique one or no. It can't have infinitely many, basically. So then A can't have infinitely many solutions. And the reason for that is we don't know anything about B. This isn't the augmented matrix. If we had B, then we would know whether or not B had a pivot matrix or had a pivot in it, and that would tell us if we have one solution or no solutions. But it's enough to know that we don't have infinitely many solutions. That's all we care about. So then, since we're in the case of not infinitely many, that means T is one-to-one. Okay. So we're about to go into some more theorems that are going to give us other ways to think about how we use one-to-one and onto, and they're really useful. They get used a lot. So theorem 11, because it's theorem 11 in your book, yay for renumbering. We have T is a linear map. We say that T is one-to-one if and only if T of x equals 0 has the trivial solution. So the reason behind saying if and only if, we're going to get formal right now, is it implies both ways. So if it's 1 to 1, then t of x equals 0 has the trivial solution. If it has the trivial solution, you go back the other way. That implies injectiveness. And so in order to prove this theorem is true, we have to prove both directions. So proof. And we're going to go in this direction first. So that means that we get to suppose, so let t be 1 to 1, and we're going to say that this equals 0. So we haven't assumed the conclusion. The conclusion would be that t of x equals 0 has the trivial solution. I'm not saying anything about the trivial solution. I just said that it was equal to 0. So in order to prove our theorem, we need to prove that x is going to be equal to 0. So what we know is since t is linear, t of 0 equals 0. And that was from the previous lecture. Let's see. Yeah, that's the previous lecture. It was an orange box. You can go find. Okay. So then t of x equals t of 0. But wait. T is 1 to 1 by assumption. So since it's 1 to 1, remember what 1 to 1 means. If the outputs are the same, the inputs must also be the same. So then we have x is 0. That's exactly what we wanted. And then just to be very explicit, then this guy has the trivial solution. Oh, only has. Okay, so that was one direction. Now we have to go the other direction. So coming back. Now we're going to assume that it has the trivial solution. So suppose that this equation only has the trivial solution. And what we don't have anymore is that it's 1 to 1. We're going to try and get that t is 1 to 1. So we're going to start with setting them equal, or setting two different things equal to each other, like this. So here we go. We've got two inside vectors, and their outputs are the same. If we can use the fact that there's only the trivial solution to get that they're equal, then we have 1 to 1. We want x1 and we want x2 to be equal to each other. We're going to have to somehow get there. And I'm going to tell you we can get there by using some properties of being linear. There's not much to do. I'm going to move it to the other side. And then this is where the properties of being linear come in. We can undo that expand form and make it compact like that. Oh, vector, vector. There we go. So we know that t of x equals 0 only has the trivial solution. That means this bit inside has to be equal to 0. So then x1 minus x2 equals 0. So then x1 equals x2. There we go. The outputs were equal, therefore the inputs must also be equal. We have 1 to 1. This gets used a lot. throughout math. So if you're going to go and do more math, be prepared. Last theorem, we've got theorem 12. We've got T is a linear map with a standard matrix A, and we have one statement for onto and one statement for one-to-one. We say T is onto if and only if the columns of A span Rm, and we have T is one-to-one if and only if the columns of A are linearly independent. So let's start with number 1. We're going to say T is onto implies that for all B in Rm, Ax equals B has a solution. And then we can go back to that theorem from 1.4, the equivalent statement of A, and we have for all B in Rm, B is in the span of A1 all the way up to AN. Where I'm being lazy, I'll put parenthetically A1 AN, so that you know that the A's are supposed to denote the columns of A. And then our handy dandy theorem, once again, the columns of A span Rm. Okay. Now we have to go the other way. We started with onto, and we got to columns of A span Rm. But I'm going to say look at these steps really closely. So columns of A spanning Rm is the same thing. It goes backwards as B being in the span of the columns of A. But B being in the span of the columns of A implies that Ax equals B has a solution. And then Ax equals B having a solution for all B implies that T is onto. So all of those steps were reversible. So this time we got 2 for the price of 1, which is really cool. And then number 2 is left to you. It is an exercise for the reader. There you go. And then that wraps up 1.8 and 1.9, and I will see you all next time.